So I like to start my talks by saying a bit about myself. I think a lot about the relationship between natural and artificial intelligence, and yes, that would be helpful. Nice, thank you. It's probably fine. If there's anything really important in that corner, it's okay. Yeah, and so I think about various aspects of this, like the kinds of learning experiences that natural intelligence has and how they might help artificial intelligence to learn, mechanisms that natural intelligence might learn to use to learn and adapt, and also I do a bit of work on analysis and theory of what deep learning models do. And the work I'm going to tell you about today is sort of falls into that latter camp, in particular analyzing what language models do. So I don't think I have to introduce to this audience or to any machine learning audience anymore that there's all these cool things called large language models now that do all kinds of interesting stuff. And if you're at all on Twitter or reading archive, you'll have noticed that there's been a lot of debates recently about what exactly it is that these models can do. And people are asking questions like, well, are these models capable of reasoning? Do they understand language? Do they know grammar? And so on, and giving various kinds of answers to those questions. But what I'd like to highlight in this talk is that these questions are kind of predicated on some either explicit or implicit comparisons to the things that we think humans are capable of and the things that we think humans are good at. And so what I'd like to do in this talk is try to raise two questions that this brings up. So the first is, how is it that we can fairly compare capabilities between humans and language models? How can we know that we're really measuring the same thing in both cases? And the second question is, well, is there even a reason that we would want to do that? What might we be able to learn by comparing humans and language models? And I'm going to try to illustrate that with a couple of case studies from some work we've done with grammar structures and reasoning in these models. Cool. So I'm going to start by giving a kind of overview about what I think the challenges and opportunities of comparing humans and language models are. And to do that, I want to take some inspiration from comparative psychology. So for those of you who don't know, comparative psychology is the subfield of psychology where people try to compare humans to animals or animals to other animals to try to understand something about the capabilities that each system has. And when people try to make these comparisons, they tend to think very carefully about ensuring that the methods they use are matched across the species. So I like this quote from some random paper I pulled up, which is that a key challenge to comparative research is making sure that any differences or similarities you discover reflect true species differences or similarities, rather than differences in the procedures you use to assess the systems. And to illustrate this a little more concretely, imagine I see this squirrel in my backyard, and I put a Rubik's Cube in front of it. And then I say, oh, the squirrel didn't solve the Rubik's Cube, so I guess squirrels don't understand relations. Well, a skeptical comparative psychologist or a skeptical audience like you might ask me a few questions like, well, did the squirrel even know what I was asking it to do? Was the squirrel really motivated to solve this task? And so in neuroscience and comparative psychology, people do things like, well, take away the animal's food for a while, and so give it food for solving the task so that's very motivated to actually do the task. And then, of course, you have to think about how you make the goal understandable to the animal, how you make the problem affordances work for the animal. Maybe it's just hard for squirrels with their cute little paws to manipulate the Rubik's Cube and so on. And so people in comparative psychology think a lot about how to give the animal the best chance it can possibly have to solve the same task that humans are solving. And so similarly, if I take a language model like DeepMind's chinchilla model here, and I put some problem in front of it like a Rubik's Cube, and it doesn't solve it, and then I say, language models don't understand relations, what I'd like to suggest is that maybe we need to ask the same kinds of questions. So how do we ensure that the model knows what we want it to do? How do we ensure that the model is motivated in some sense? And what I mean by that is that these models are trained to model a very broad distribution of language. And so you can imagine there's some latent variable that the model is representing that corresponds to sort of what kind of language it's trying to model at the present moment. And that could correspond to, correct answers or solving relational questions correctly, but it can also correspond to things that you observe all the time on the internet, like sarcasm or memes or other things that don't necessarily correspond to correct answers. So if you want to get the best answer from the model that you can, you need to think about how you can push it into the part of the distribution where it wants to produce the correct answer. And if you have any suggestions for how to talk about that in a less anthropomorphizing way, I would be very open to hearing it. Okay, yeah, and then similarly to animals, you need to think about how you ensure that the goal of the question is clear to the model, how you make sure that the affordances of the question work for the model as they do for humans, and so on. That is, just as for animals, how do you give the model the best opportunity possible to demonstrate its capabilities? So that's the first question I'd like to bring up. What evaluation methods will allow us to make fair comparisons between humans and language models? And I'm not the first person to raise this question. So Chaz Firestone has this nice paper on the performance and competence in human-machine comparisons, which focuses more on the vision side, but tackles some of the same questions. And he highlights this distinction between performance and competence. How many people in the room are familiar with that term, performance competence distinction? None. Okay, that's good, because that means this isn't a linguistics audience. So the performance competence distinction comes from Chomsky. And the basic idea is that competence is some underlying capability that a system has, like the ability to process true recursion, let's say. And performance is how that system actually does on some task that requires recursion. And the point that Chomsky made when he was proposing this distinction is that, of course, human performance might be affected by lots of things besides our true underlying competence, like working memory constraints, or the fact that we're distracted, or the fact that we're bored, or the fact that we don't care about answering questions, or whatever, right? And so Chomsky kind of proposed this distinction to try to argue that humans do have a true competence for recursion, even though they don't always show it. And of course, there's lots of issues with trying to make this distinction between competence and performance. In particular, it leads to kind of unfalsifiable claims, because you can always dismiss any failure as, oh, that's just performance, it's not about the real competence. But I think the general point that there's, sometimes a system will make errors that are not errors of some true underlying knowledge, but are rather more superficial, is important. And it kind of relates to what I was saying before about the animals and the comparisons. But to step back and think about this a bit more philosophically, I think it raises some questions about how we even think about what it means for a system to have a capability or a competence. And so one way you could frame this is that, oh, a system is capable of doing something if it succeeds even in the worst case. And people who are skeptical about computer vision systems often give this sort of, implicitly assume this sort of definition of competence. Like they'll say, if a system fails at adversarial examples, that means it doesn't really have a capability of doing vision, right? It doesn't have a real capability unless it succeeds even in the worst case examples. But I think when we talk about humans, we'll often ascribe a capability to a human, even if they don't do it all the time, even if they only do it sometimes, right? Like we would say a scientist can revolutionize a field, even if they've only done it once, or maybe if they've never been able to do it at all, but they could have that potential. Or you could, of course, think about a capability as some sort of behavior and expectation, but then you run into all sorts of issues like, well, what if there's these weird examples, like adversarial examples that break things? So what distribution are you taking expectation over, and so on. Anyway, so I think that there's some deep kind of unanswered questions about what it means for a system to even have a capability. I'm not going to try to answer those questions, but what I would like to highlight here is that in cognitive science and neuroscience, comparisons between different systems have often helped us to understand what our capabilities are. So for example, comparing humans to animals has shaped the way that we think about how humans process recursive language structures, and comparing humans to normative computational or theoretical models has helped us to think about human reasoning, in particular thinking that, well, maybe humans are like trying to approximate a normative model as best they can with the limited resources that they have. And so the question that I'd like to raise then is, well, what I'd like to suggest is that because humans and language models are very different systems, making comparisons between them could also perhaps help us to understand some of the capabilities of each system better. All right, so that's enough motivational stuff. Let's get into some actual results. But let me pause here and see if there are any questions first, or if anyone wants to pick any arguments immediately.
I mean, maybe you have had this response to this. Like, I agree with the competence performance distinction, but maybe in evaluating models, sometimes the only important thing is performance in a sense. Like, it might have the competence, but what does it matter? Like, is there also an aspect of evaluating how hard it is to motivate it in a sense?
Yeah. So I mean, I think that's a great question. Of course, it applies to humans too, to some extent, right? And if you're, for example, if the reason you care about the performance of a model is because you're trying to decide whether you want a human to do this task or a model to do this task, then there's sort of motivational constraint, or the like performance motivation interaction on both sides is relevant, right? I think that if all you care about is performance, it's still, the performance competence distinction still matters insofar as perhaps there are factors that you haven't considered that would push that performance up, right? So like, if you think of competence as being the, best case, what the system could do on every question under some sort of constraints, which I'm not fully articulating right now, then you could think like, that's what we, at least some sort of notion of competence is what we care about, right? Like it's like, if I give the language model a really bad prompt and it does poorly, that isn't necessarily relevant for telling me about like how useful that model could be. But it's a tricky, it's a tricky trade-off. And certainly to some extent, what we care about is performance ultimately over some distribution.
Yeah.
Cool. Any other questions? Awesome. So let me dive in and tell you a bit about recursive grammar structures. So, right. So in particular, in this work, we looked at this type of grammar structures called center embedding. And these structures are a pretty simple thing. This arrow is kind of blocked here, but center embedding is when you take one sentence, one clause of a sentence, and you embed it in the center of another clause. And so the way that this works is maybe you have a clause like the keys, or a sentence like the keys are heavy. And then you can take some other clauses and you can put them in the center, like the keys that the man near the cabinet holds are heavy, right? And so that's center embedding. And the interesting thing about it is that it's sort of a recursive construction, because you sort of have this dependency between the noun keys and the verb are that you have to pop back up the syntax tree to handle, at least if you're processing the sentence in the kind of way that Chomsky thinks that you would. And so, right. The interesting thing about this, and the reason it's been kind of an important case study in linguistics, is because this is one of the rare cases when you have this nice, strong dissociation between linear distance in a sentence, that is how close two words are to each other in the sentence, and how close together they are in the syntax tree, right? So there's this strong dependency between the keys and the verb are that has to agree with the noun keys. But no matter how much stuff you put in the middle between them, no matter how much stuff separates them, you have that same grammatical dependency there. And so the model or a human has to pay attention to that same dependency. And so because of this, these kinds of sentence structures have been a key area for historic debate about the capabilities of neural networks versus more structured grammar systems. And there's also been some interesting newer work on this topic. And so I was actually quite excited to see this paper come out that said causal transformers perform below chance on these constructions, unlike humans. But after reading the paper, the question that came to me is, well, was the evaluation they did fair? And so let me walk you through why I had that concern. So in this paper, they evaluated some humans on some tasks, and they evaluated GPT-2 on some tasks. And there we go. So, the people who wrote this paper are pretty experienced cognitive scientists. So they presumably took out the experimental psychology textbook, and they wrote a fairly long methods section for how they evaluated humans. And I'll pull out some details of it for you. After each trial, participants received feedback concerning their response. At the beginning of each session, participants performed a training block comprising 40 trials that covered all stimulus types. For the language model, well, there isn't a textbook on experimental AI yet, as far as I know. And so the authors, I guess, wrote a pretty short methods section. And in particular, they evaluated the model without any prompt or training trials or instructions or context. And so this raises the question relating to that comparative psychology work. Well, is there a real difference in capabilities that the authors have observed here? Or is it just a difference in the experimental methods they used to evaluate the two systems? So one of the things that I did in this paper was to evaluate language models with a bit more context. So here on the left, I'm showing you the results from this original paper, the human error rates on these center embedded dependencies. And there's a bunch of different conditions that I'm not going to go into the details of what they are. But what you can see is that generally across all the conditions, human error rates are below-ish chance, and chance is 50% there. And oh yes, these are error rates, so lower is better. Okay, so this is the performance if we evaluate chinchilla zero shot on these same conditions. And what you can see is that although the model's doing pretty well on many of the conditions, there's these two particularly challenging conditions where it's performing worse than chance, again, as the authors had found in their original paper with GPT-2. But if we give chinchilla a couple of sentences in the prompts that are grammatically correct, all of a sudden it gets much better, is above chance in all conditions. And if we give it 8 examples, it's actually performing very well indeed. And so to put that another way, if we give chinchilla one-fifth of the sentences that the humans received in their training trials, we don't give it any training examples in the hard test conditions, it actually performs comparably in the hardest conditions to the way humans perform in the easiest conditions. Okay, and of course we can do things like make this task even harder by adding some extra layers of embedding to the sentences. Chinchilla still does better than the humans and so on. The second thing I did in this paper was to just look at the human data, and it turns out that if you look at it carefully, maybe the humans are not doing so well early in the experiment, maybe they're learning over the course of the experiment. Fine. The point is that, well, language models might actually be able to match the human capabilities for recursive grammar, but you need to think carefully about your comparisons to realize that, or at least need to think about them a little bit. Okay, so to sum up that first part, I think it's important to think carefully about making comparisons between humans and language models if you want to make them, just like we do in comparative psychology. In particular, you want to think about making sure that the tasks are fairly matched in how they motivate the task, how they set up the task for the two systems, and so on. And although this is a relatively egregious example of a difference in that, I think it's much more common in the literature to have sort of subtle errors. Like, yes, there's often examples where people give a language model a zero-shot task and humans get some more instructions or examples, but also there's more subtle issues in sort of like humans' ability to, think before responding. Maybe that's not quite a fair comparison to a language model that's not given chain of thought, and so on. Okay, yes. I think if you're not interested in linguistics, you should probably just ignore this center point, and actually that one too. But basically, I'm just saying this relates to some old debates about recursion and Chomsky's idea of merge and so on. One point I would like to touch on here is why I think this is kind of a natural thing to slip into, at least from a cognitive science perspective. And it's because cognitive scientists are used to analyzing a relatively different kind of models than they have ended up analyzing now. And in particular, cognitive science has been working for a long time with models that are kind of like this, like toy models that are trained to do some particular task and are analyzed for their performance on that particular task as a model of that particular task. So for example, this is a very old connectionist neural network model that was used to, among other things, model processing of these kind of grammar structures. And for cognitive models like this, it makes sense to do zero-shot testing of the model because the model is already sort of motivated for the task because that's exactly the task it's been trained to do, right? But for a foundation model, like a language model, again, it's trained to approximate a much broader distribution of language, including different, dialects, memes that might not have perfect grammar, and so on. And so we need to think a little bit more carefully about doing the analysis. And I think people often conflate these two models in cognitive science. Cool. Great. Question.
So would instruction following help you?
Yeah, that's a great question. So I think that an instruction-tuned model would probably be better at this. It's not entirely clear to me that instruction tuning gets you the best of the capabilities of the model in all cases, right? And I think it'll depend a lot on the kind of data set you're tuning on. So
when does it not give the best performance?
Right. So for example, let me actually illustrate it with a case of RL tuning, a thought study on RL tuning rather than instruction tuning, but I think a similar kind of argument would apply. Let's imagine you're doing tuning with human preferences on a model, and let's imagine further that this model is using that to sort of like select which part of the latent distribution it's sampling from in this sort of thought experiment. If your human...
By latent distribution, you mean distribution over output tokens? Or...
Yeah, the distribution over language, but let's say that there's some higher level features. Okay, let me make this more concrete. Imagine that you have, like, in your language model has inferred that there's 50 different speakers of the language, and it's just deciding which of those speakers it should sample. And so maybe when your human preferences say, oh, you know, I like this answer over that answer, it's because that answer is simpler and easier to understand. And so you'll be selecting for the speaker of the language who produces the simplest, easiest to understand answers, and that might be correlated with the speaker who's most likely to produce the correct answers, but probably won't be perfectly correlated with it, right? And so I think that there's some potential for at least these preference tuning kinds of things to introduce a bias towards certain parts of the language space that won't necessarily give the absolute best answers. And similarly with instruction tuning, I think that maybe, you know, the kinds of data sets you train on will bias the model towards being more accurate on certain kinds of questions. And maybe if you don't cover other parts of the space well enough, you'll actually bias away from accuracy on those if those kinds of accuracy in those two spaces is anti-correlated. Does that make sense?
Yeah, it makes sense. Thank you.
But yeah, in general, I think instruction tuning should help. Okay, so the second study I'd like to tell you about, and maybe the more exciting one from my perspective, because grammar is kind of whatever, is about content effects on reasoning. So if you ask yourself what's reasoning, and maybe like any reasonable person, you go look it up on Wikipedia, what you'd find is something that, like, reasoning is something like a uniquely human capability for applying logic to arrive at a conclusion or something. But in the cognitive science literature, there's been a fairly extensive debate about the extent to which humans are actually logical reasoners, or whether we're using some more heuristics and biases and not really doing rational things most of the time. And one key feature of this debate has been this distinction between abstract logic versus the effects of content on reasoning. So logic itself is independent of content. That is, if I give you a logical proposition like, if not X, then not Y, then no matter what X and Y refer to, that will always have certain logical consequences, right? And so a system that reasons abstractly, that is, a system that reasons without using only the logical structure, not the content, is guaranteed to be systematic. That is, to always give you the same conclusion from the same logical structure. So the question is, do humans exhibit abstract reasoning in that sense? That is what's going on in our heads more like some sort of propositional inference or something a little bit messier? And I'm going to give you two examples that suggest that it's at least a little bit messier from the classic cognitive science literature. So the first is that people judge arguments by their content, not just by logic. So if you ask people to judge a syllogism for whether it's logically valid or not, turns out their answers are biased by their beliefs about the conclusion. So for example, here's a syllogistic argument. All students read. Some people who read also write essays. Therefore, some students write essays. Quick, raise your hands. Is this a valid argument or is it invalid? Okay, most people say invalid. Good. And here's another argument. All students read. Some people who read are professors. Therefore, some students are professors. Well, if you ask the average person on the internet to judge whether this first argument is valid, you'll maybe get sort of a mixed distribution of answers. But if you ask people to judge this one that has the same logical structure, people are very, very likely to say that's an invalid argument because the conclusion just seems so implausible that forces you to think about it, right? And so in a bunch of classic papers on this topic, people have shown that there's this sort of conflict between logical reasoning and belief in how people judge syllogisms. And I want to show you these numbers because they're really kind of shocking. So these are the percentage of subjects who say that an argument is valid based on whether the conclusion is believable in this column or unbelievable, whether the argument is actually valid in the top row or invalid in the bottom row. And the point is that if the conclusion is believable, 92% of the time, regardless of whether the argument is actually valid, people are like, oh yeah, that seems like a valid argument. And if the conclusion is unbelievable, then you see some more sensitivity to the logical structure. So people can pay attention to the logical structure if a surprising conclusion pushes them to do so, but they're strongly biased by the content in the extent to which they do pay attention to that.
Can I ask a question?
Yes.
Did you try to tell them like reason logically?
I didn't try telling them let's think by step, partly because this study was run long before I was born. But yeah, that's a good question. So people have tried a bunch of different things in these kinds of studies, and I don't remember for these particular things, but in general, in the space of issues, telling people to slow down and think more carefully does improve performance on these things, but it doesn't wash out the biases entirely. But yes, great question. People are sensitive to that. But one thing I want to highlight is that these kind of content effects on reasoning are not just a bias that always harms our reasoning. And in fact, it can facilitate our reasoning in certain kinds of cases. So this even more classic study by Wei-san looks at how people are able to reason about a rule. And the way it works is as follows. So you show people some cards like these, where each card has a number on one side and a color on the other side. And you ask them, well, which cards would you need to flip over to check if the following rule is followed? So if the card shows an even number on one side, then it has the color red on the other side. Okay, quick, which cards do you need to flip over?
8 orange.
8 orange? You know. 3 red? All right, so there's a few different answers. It turns out that 8 orange is the correct answer, but it's not if you asked most people on the internet this question, they won't get that. They will tend to say that you should flip over 8 and red. And there's been various explanations for this, which I'm not going to go into. But you can take this same logical structure and you can just put some slightly more familiar content into it, and then it's much easier. So for example, you can say, oh, each card has an age on one side and a drink on the other side. Which cards do you need to turn over to check the rule that if you're drinking an alcoholic beverage, then you're over 21 or 18, I guess, because we're in the UK, then everybody gets the question correct, or not everybody, but many people. So familiar content can also help facilitate reasoning. Unlike in the syllogisms problem, it can help us to reason about situations that are more complicated. Cool. So in both these cases, though, it seems like human reasoning is not fully abstract. Instead, it depends on the content that we're reasoning about. So in the last few years, there's been quite a bit of interest in language model reasoning. And I would say that these papers on this subject kind of fall into a spectrum as well. That ranges from language models are capable of reasoning to language models are just using a pile of heuristics and tricks and biases. For example, this paper, which is a very nice and interesting paper, notes that language model reasoning accuracy is correlated with how frequently the things that it's reasoning about occur in the training corpus. And so if you think about that sentence for a second, it's kind of like the sort of effects that humans show, where they're biased by how frequent or familiar a situation is, how believable a situation is, and they tend to reason better about the situations that are familiar. And so what we wanted to ask in this project was, will language models show the same kinds of content effects on reasoning as humans do? So to assess this, we put together some data sets for evaluating this, where we created new problems that are like the syllogism problems and the Wei-san rule problems that have been evaluated in prior work, but they're new so that we're fairly sure they're not in the training corpus, at least not in exactly this form. Created these across a variety of conditions. And I'm just going to tell you about a few results from that today. So for the syllogisms tasks, we set the problem up like this. We give an argument, syllogism, so it has 2 propositions and a conclusion. And then the model is given a forced choice between the answers, this argument is valid and this argument is invalid. And if we give the chinchilla language model this task 0 shot, what you can see is that consistent things that we think are consistent with human beliefs are plotted in this sort of mint color here. Things that we think violate human beliefs are plotted in this sort of cranberry color. And you can see that there's this strong bias by believability. So I'm plotting, sorry, I should have said that before. I'm plotting the proportion of the time the model answers valid. And what you can see is that the model is answering valid almost all the time in the conditions where the conclusion is believable. And it's answering valid much less when the conclusion is unbelievable, but it's showing a little more sensitivity to the logical structure. And if you compare those bars to the numbers I showed you earlier, they're actually a pretty shockingly good fit. So like humans, the model is very biased by believability, shows a bit more sensitivity to logic when the conclusion is unbelievable. So next on the Wason task, these problems are a little more involved, but we give the model some sort of text that includes the rule and so on. We show it some cards, and then we give it a forced choice over different sets of cards it could flip over. And again, if we compare the model on the two conditions that have been evaluated in humans, the realistic rules, the model is much more accurate at than the arbitrary rules that involve sort of abstract concepts. And there's also some other interesting patterns in the data, like these shuffled realistic rules that actually the model does above chance on as well. And to get back to the asking humans to think step-by-step question, that can help humans in some cases, and also for the models, doing things like giving them few-shot examples of the task, or giving them a prompt that just says something like carefully evaluate these logical arguments, or reframing the problem to have a slightly different structure can help them to perform better. But generally, these kind of interventions help more with easier cases rather than harder ones like the Wason task. And that actually kind of fits with the human literature, because in the Wason task in particular, it's quite hard to get average people to do this task well. But one thing that you can do is to give people a good 10 to 12 years of math education, and then people get pretty good at that. And that's perhaps why people were pretty good at these questions in this audience. Okay, but so the point is that language models show human-like content effects on reasoning about rules and syllogisms. And I think what this offers us is actually an opportunity to reflect on what reasoning itself is. What is this capability? So both humans and language models, in some cases show some things that we might kind of think of as reasoning, and in some cases seem to be doing things that are more like a pile of tricks. And I guess what I'd like to suggest, and I'm certainly not the first person to suggest this, is that there's kind of a false dichotomy being posed here, right? Why is it that humans and language models might show these effects? Why wouldn't we be perfectly logical? Why wouldn't we evolve to be perfectly logical? Well, it's because reasoning isn't an end unto itself, right? Evolution is not selecting for reasoning to be logical. It's selecting for us to do well at solving tasks, solving real world situations, right? And so maybe content affects human reasoning, because if we're biased towards reasoning well about frequently occurring situations, well, that helps us over the distribution of situations that we encounter every day, right? And similarly for language models, maybe content affects the answers they give on these kinds of reasoning tasks, because those kinds of content effects allow them to make correct predictions more often over the distribution of language that they encounter on the internet. And of course, yes, as I said earlier, this is not a new idea. There's a lot of cognitive accounts that have kind of fit in with this, including the idea of bounded rationality. But I think that thinking about it from the language model perspective can maybe help us to get a more general sense of the way in which that these kinds of content effects could be normative. They could be a more general kind of just trying to do better across a broad distribution. So with that, I'd like to provide some closing thoughts, and then we can have lots of discussion. So I started this talk by trying to highlight some of the challenges of comparing language models and humans, in particular, the fact that it can be difficult to make a fair comparison between humans and models, that we need to ensure that we match the task communication and affordances and so on. And I think this goes beyond just matching the instructions or examples, and might be something that requires research in its own right, just like comparative psychology has sort of iterated fairly carefully on how you get an animal to do a task well. But I'd like to suggest that comparison can offer us an opportunity to achieve a better understanding of the capabilities that we have. So language models are exciting in part because they can perform many of the tasks that humans can do from the same stimuli, at least in some cases. And they can help us to think about how these phenomena like reasoning could emerge from a relatively simple process of prediction. And I think that because they have such a different architecture to humans, they can actually help us to reveal stronger constraints on where this behavior comes from, right? An opportunity to ask what is the same between the experience of humans and these systems. And one work that I'd like to highlight here is this work that my colleague Stephanie Chan led on looking at how properties of natural data might be what leads to in-context learning in transformers. And I think that one of the exciting things about language models is they offer us this really powerful opportunity to drill in and ask why questions about how data contributes to what a model does or what a system does. And of course, these systems differ from humans in many places. That provides an interesting opportunity to ask where language models and humans diverge. Like, are there cases where grounding is really important or where interaction is important? What are the things that these models are missing and what aspects of their experience might contribute to that? And yeah, so that's basically all I had to say. I'd like to thank my colleagues who worked with me on some of these projects, and particularly Ishita Dasgupta, who was co-lead of the second project on content effects, as well as Stephanie, Tony, Jay, Darsh, and Felix. And thanks to you all for listening. Happy to take more questions.